How CAN handles errors. Error handling is built into the CAN protocol and is of great importance for the performance of a CAN system. The error handling aims at detecting errors in messages appearing on the CAN bus, so that the transmitter can retransmit an erroneous message. Every CAN controller along a bus will try to detect errors within a message. If an error is found, the discovering node will transmit an error flag, thus destroying the bus traffic. The other nodes will detect the error caused by the error flag, if they haven't already detected the original error, and take appropriate action, that is, discard the current message. Each node maintains two error counters, the transmit error counter and the receive error counter. There are several rules governing how these counters are incremented and/or decremented. In essence, a transmitter detecting a fault increments its transmit error counter faster than the listening nodes will increment their receive error counter. This is because there is a good chance that it is the transmitter who is at fault. When any error counter raises over a certain value, the node will first become error passive. That is, it will not actively destroy the bus traffic when it detects an error, and then bus off, which means that the node doesn't participate in the bus traffic at all. Using the error counters, a CAN node can not only detect faults but also perform error confinement. Error detection mechanisms. The CAN protocol defines no less than 5 different ways of detecting errors. 2 of these work at the bit level, and the other 3 at the message level. Number 1 is bit monitoring, 2 is bit stuffing, 3 frame check, 4 acknowledgement check, 5 cyclic redundancy check. Number 1, bit monitoring. Each transmitter on the CAN bus monitors, that is, reads back, the transmitted signal level. If the bit level actually read differs from the one transmitted, a bit error is signaled. No bit error is raised during the arbitration process. Number 2, bit stuffing. When 5 consecutive bits of the same level have been transmitted by a node, it will add a 6th bit of the opposite level to the outgoing bit stream. The receivers will remove this extra bit. This is done to avoid excessive DC components on the bus, but it also gives the receivers an extra opportunity to detect errors. If more than 5 consecutive bits of the same level occurs on the bus, a stuff error is signaled. Number 3, frame check. Some parts of the CAN message have a fixed format, i.e. the standard defines exactly what levels must occur and when. Those parts are the CRC delimiter, ACT delimiter, end of frame, and also the intermission. But there are some extra special error checking rules for that. If a CAN controller detects an invalid value in one of these fixed fields, a form error is signaled. Number 4, acknowledgement check. All nodes on the bus that correctly receive a message, regardless of their being interested in the contents or not, are expected to send a dominant level in the so-called acknowledgement slot in the message. The transmitter will transmit a recessive level here. If the transmitter can't detect a dominant level in the ACT slot, an acknowledgement error is signaled. Number 5, cyclic redundancy check. Each message features a 15-bit cyclic redundancy checksum, or CRC, and any node that detects a different CRC in the message than what it has calculated itself will signal a CRC error. Error confinement mechanisms. Every CAN controller along a bus will try to detect the errors outlined above within each message. If an error is found, the discovering node will transmit an error flag, thus destroying the bus traffic. The other nodes will detect the error caused by the error flag, if they haven't already detected the original error, and take appropriate action, that is, discard the current message. Each node maintains 2 error counters, the transmit error counter and the receive error counter. There are several rules governing how these counters are incremented and/or decremented. In essence, a transmitter detecting a fault increments its transmit error counter faster than the listening nodes will increment their receive error counter. As was mentioned, this is because there is a good chance that it is the transmitter who is at fault. A node starts out in error active mode. When any one of the 2 error counters raises above 127, the node will enter a state known as error passive, and when the transmit error counter raises above 255, the node will enter the bus off state. An error active node will transmit active error flags when it detects errors. An error passive node will transmit error passive flags when it detects errors. A node which is bus off will not transmit anything on the bus at all. The rules for increasing and decreasing the error counters are somewhat complex, but the principle is simple. Transmit errors give 8 error points, and receive errors give 1 error point. Correctly transmitted and/or received messages cause the counters to decrease. Example, slightly simplified. Let's assume that node A on the bus has a bad day. Whenever A tries to transmit a message, it fails for whatever reason. Each time this happens, it increases its transmit error counter by 8 and transmits an error active flag. Then it will attempt to retransmit the message, and the same thing happens. When the transmit error counter raises above 127, that is after 16 attempts, node A goes error passive. The difference is that it will now transmit passive error flags on the bus. A passive error flag comprises 6 recessive bits and will not destroy other bus traffic, so the other nodes will not hear A complaining about bus errors. However, A continues to increase its transmit error counter, and when it raises above 255, node A finally gives in and goes bus off. What do the other nodes think about node A? For every active error flag that A transmitted, the other nodes will increase their receive error counters by 1. By the time that A goes bus off, the other nodes will have a count in their receive error counters that is well below the limit for error passive, that is 127. This count will decrease by 1 for every correctly received message. However, node A will stay bus off. Most CAN controllers will provide status bits and corresponding interrupts for 2 states: error warning, 1 or both error counters are above 96, or bus off, as described above. Some, but not all, controllers also provide a bit for the error passive state. A few controllers also provide direct access to the error counters. The CAN controller's habit of automatically retransmitting messages when errors have occurred can be annoying at times. There is at least one controller on the market, the SJ1000 from Philips, that allows for full manual control of the error handling. Bus failure modes. The ISO 11898 standard enumerates several failure modes of the CAN bus cable. 1. CAN high interrupted. 2. CAN low interrupted. 3. CAN high shorted to battery voltage. 4. CAN low shorted to ground. 5. CAN high shorted to ground. 6. CAN low shorted to battery voltage. 7. CAN low shorted to CAN high wire. 8. CAN high and CAN low interrupted at the same location. 9. Loss of connection to termination network. For failures 1 through 6 and 9, it is recommended that the bus survives with a reduced signal-to-noise ratio, and in case of failure 8, that the resulting subsystem survives. For failure 7, it is optional to survive with a reduced signal-to-noise ratio. In practice, a CAN system using 82C250 type transceivers will not survive failures 1 through 7, and may or may not survive failures 8 through 9. There are fault-tolerant drivers, like the TJA 1053, that can handle all failures though. Normally you pay for this fault tolerance with a restricted maximum speed. For the TJA 1053, it's 125 kilobits per second.